When we use lenses and mirrors to manipulate rays of light, they can have various effects on the image. They can magnify or reduce the image, they can invert it, or they can place the image at a certain location in space, which is different from where the object or the lens or mirror is. In this video, I'm going to show you how to use ray diagrams to predict and explain these effects. Let's start with a simple example of the location effect. I've turned off the autofocus on my webcam right now so that it's focused at the distance of my face. If I move my finger closer to the camera, you can see that it gets out of focus and blurry. With this book, if I put this book at about half that distance, it's out of focus and it's very hard to read that small font because it's out of focus. I've got my daughter's compact here that I guess she forgot to take with her when she moved out of the house. If I put it right there at half the correct distance, the print on the back is out of focus. But now if I hold the mirror at the same position, you can see that the image of the webcam's self in the mirror is in focus. So what that tells you is that that image is not located here in the plane of the mirror. That image, if it's in focus, must be located farther away. It's located at the distance that the webcam is currently focused to look at, which is back here. So the webcam's image appears on the other side of the mirror, equally far behind it. Now let's use a ray diagram to understand that observation. Here's my mirror, and the object, which is the camera itself or its housing, would be some kind of a rectangular shape over here. But in a ray diagram, we're normally only interested in drawing a ray diagram for one point. So I'm going to pick one point on the camera. And the point that I've picked is one that's on the line that goes perpendicularly through the center of the mirror. That's the optical axis. There's never any reason to pick anything that's not on the optical axis if you can avoid it. It just makes things harder. Rays are going to come out in all directions from that point on the object because this is diffuse reflection. And out of all of the rays that we could draw, certainly the easiest one is going to be the one that goes directly on axis, hits the mirror perpendicularly and comes back like that. The image is going to be wherever the rays that have been reflected cross or appear to have crossed. That means we need two lines so we can find their intersection or where they appear to have intersected. We need to pick one other line now. I'm going to arbitrarily draw that one out of all the rays I could have picked that hit the mirror in different places. It gets reflected at an equal angle on the other side of the normal. And now I have these two representative rays coming off of the mirror. When your eye sees those rays, your eye doesn't know that anything happened to them in the past. It doesn't know that they bounced off of a mirror or anything like that. So if you ask your eye where they came from, it's going to think they came from somewhere like that, where those rays both look like they came from. So to show that on the diagram, we use dashed lines. The dashed lines are the imaginary traceback of where rays appear to have come from in the past. And it's also important to understand that in this kind of ray diagram, if we're going to claim that this point is an image because the rays appear to have crossed there, the rays we're talking about need to be rays with the same history. So this is a ray that has been reflected once from the mirror. This is also a ray that has been reflected once from the mirror, so they have the same history, and that means it makes sense to have them form an image. We can see that the image is equally far on the other side of the mirror. You could prove that geometrically if you care about rigor by proving that this triangle and this triangle are congruent. So I've got an object point here and an image point here. This image is a virtual image because the rays only appear to have crossed there. No light actually got through the mirror. No rays actually crossed back there. And it's important to understand that that is the criterion for a real image as opposed to a virtual image. Real is if the rays really cross, virtual is if they don't really cross. Sometimes students try to memorize rules like It's virtual if it's on the front or the back or something like that. Those rules are not in general correct, and they would be different for lenses and mirrors. Just remember that virtual is when they don't really cross. The main point of this was to show the location of the image. So to an observer over here, that image appears to be far away. And that was why the image of the webcam itself appeared to be in focus in the video. One thing to understand that may be conceptually unclear because of the way I set this up is that it's only a coincidence that I used the webcam to observe itself, which is kind of a weird thing. You might want to think of it just like the webcam's eyeball is observing the webcam's frame, which is a separate object. In general, on ray diagrams, the observer is not part of the diagram. And in general, an object point like this is not an eye or anything like that. And one way to see that makes sense is that, for instance, if you're burning ants with a magnifying glass, it doesn't matter whether there's an observer. If no one's looking at it, the ants are still burning up. In addition to the main point about the location of the image, we can see a couple of other things here. One thing is we can understand why the magnification of that image is neither a magnification nor a reduction. It's a magnification of 1. And the way to tell that is that this object distance and this image distance are the same. So when you look in the bathroom mirror and you see mirror world back there behind the wall, mirror world is a certain size compared to the real world. And mirror world is consistent in all of its dimensions. It's got the same magnification along that axis, and the axis perpendicular to the page. So if we've determined that horizontal distances are the same in mirror world as in our world, then we also know that vertical distances would be the same in mirror world as in our world. Finally, we can demonstrate that this image is not inverted. This is a particular system for using ray diagrams that I'm teaching you here. And in my system, we use certain tricks to make sure that we get the right results. So in this example, what we want to do is we want to find what would happen if we had another point off axis. The image that we saw actually was uninverted, so apparently the image point of that red point was right side up, so above the optical axis. So that is a reason now why we want to consider an off-axis point. And then in the system that I'm teaching you, the trick for getting accurate answers, or one of the tricks, is that when you do a different point like this, still make that point send its rays to the same points on the mirror. So if I send a ray to that point on the mirror, I can do that because rays come out in every direction out of there. So I'll just pick the one that happened to hit the same point. Well, it's particularly easy to draw the reflection of that one accurately because I know that those angles above and below the axis are going to be equal in specular reflection. And then, without even drawing a second ray, I know that the image of the red point has to be above the axis because the dashed line traced back would be back here above the axis. Similarly, if I take this point and send the ray to that point on the mirror, then it's reflected like that. So when we have specular reflection like this, it's like a fan-in, fan-out kind of thing. It's like opening and closing scissors, because both of those rays have to have the same angle on both sides of the normal. And again, the trace back of this ray does trace back to a point here, not way down here. So there's the second object point, O prime, second image point, I prime, and we found that I prime is definitely above the axis. And one of the principles here in drawing these ray diagrams is feel free to cheat. So I knew that a vertical image plane on in front of the mirror, or excuse me, a vertical object plane would be a vertical image plane in the back of the mirror. Therefore, I just picked a point right above there. If I was trying to draw this super accurately with a protractor or something, the place where these lines crossed might have been here or here, and it could have been a little bit off, but I know what's going to happen, so I forced that to happen. Now let's do an example with lenses. Most students find those harder to draw as ray diagrams. I'm going to play the same trick again by using the fixed focus rather than the autofocus on my webcam. Right now it's focused at about the distance of my face. Now I'm going to put the focus a little farther away. It's focusing basically at infinity now. And this is the kind of thing that you would do kind of naturally if you were trying to look at that wall on the other side of the room behind me, where there's a lamp. Behind the lamp there's a old-timey picture of a buffalo, and you can also see a cupboard back there. So the buffalo is in focus right now. Now I'm going to change the focus so it's much closer. So the buffalo is knocked out of focus. My face is actually a little bit out of focus right now. But if I put my finger there, it's in pretty good focus. So this is the kind of thing that your eye would do naturally for you. If you were going to look at your own fingertip close up, stuff farther away would go out of focus, just like this. So the buffalo is out of focus. And I'm now going to take my other pair of glasses that I had around here, and I'm going to hold them in front of the webcam. And now I think you can see that my glasses are dirty. But you can also see that the buffalo is in focus. So let's try to explain that with a ray diagram. So way over here is that buffalo. Even though I told you only to worry about one point on the object, I feel like I have to try to draw a cute buffalo. Here we go. That's pretty good. So we're going to pick one point on the buffalo's face as our object. And the simulation that I was doing with the web camera's focus too close, that's exactly the situation that you're in if you're nearsighted, like most young people like me, and you then can't see far away without your glasses. So that's why my glasses worked for this. So because I'm nearsighted, my glasses are a diverging lens. If you look at this type of lens on eyeglasses, usually it's concave on one side, convex on the other, but the important thing is it's thinner in the middle. That's the crucial difference that makes it end up being a diverging lens. So we've got an on-axis point, because we always use an on-axis point because they're easy. If I now draw a line from the buffalo, it's going to pass straight through the lens. It won't get refracted at either the front surface or the back surface just by symmetry, because it's entering along the normal and exiting along the normal. Now we need to do a second ray that hits the lens somewhere else. So there's my kind of arbitrarily chosen second ray. And by default, if there had been no lens, that ray would have gone straight. It's sort of like Newton's first law. But because there's a lens, and because this is a diverging lens, what happens is the ray bends outward. So I'm going to make that ray end up being bent outward like that. So here are my two rays coming out. I'm not going to worry about trying to draw all the details of the refractions inside the lens. We're normally not concerned with that for the purposes that we're doing right now. So if your eye sees these rays, your eye doesn't think they came from way back here. Your eye thinks they trace back to somewhere right about there. So I'll draw the imaginary dashed line trace back of that one. The trace back of this one will be right on top of itself. And so here's the image location. And what we see here is that the image is much closer to the camera than the object was, and that's why the camera saw it in focus. Now let's do a couple of examples with this converging lens. If I hold the lens right about here and put my hand back here, you can see that the image of my hand is inverted. Now if I move my hand closer to the lens, at some point everything goes crazy, and as I keep on moving my finger closer to the lens, you can see that my hand is now not inverted in the image. So we saw two qualitatively different cases there. There was the case where the image was upright, and there was the case where the image was inverted. So that clues us in that there are going to be two different types of ray diagrams we're going to have to draw here. So here's my converging lens. The case that I did first was where my hand was far away from the lens, so I'll draw my hand back here. And there's the on-axis ray, and here's an off-axis ray. And then in this situation where the hand is very far away, this cone of rays coming out of the hand is not spreading very wide. It's a narrow cone. Therefore, the lens is strong enough to bring them back and reunite them at an image point right there. So this is a real image, and if we want to see why it's inverted, we can take an off-axis point like this, and the easiest ray to draw is the one that hits the center of the lens. What happens when you hit the center of the lens is that at the center of the lens, the front and back surfaces are basically just parallel, like a flat pane of glass. Therefore, that ray, it wiggles a little bit, does a little bit of a dog leg, but essentially it just comes out without being deflected at all. So we can tell from that that the image point corresponding to this object point has to be below the optical axis. We know that objects in the same object plane get imaged in the same image plane, so it's going to be directly below that one. And if we want to, we can draw in another ray, even though we've already convinced ourselves of where the image should be. For the other ray, as usual, I'm going to draw a ray that happens to hit the same point on the lens. Since I know where the image is, I'm going to go ahead and make it go there. And what you can see for both of these cases is that as we twist the incoming ray from, say, here up to there, the outgoing ray twists with it in the same direction. So as we go here from black to red for the incident ray, that's counterclockwise. Black to red is counterclockwise. So it's acting like a physical object. It just goes from there to there, kind of rigidly. Similar deal up here. I've got my two rays initially like this. This is the black rays that come in and out near the top of the lens. When I go to the red, it just does this, just like a rigid object. So it's not 100% exactly true that it just rotates like that, but it's actually a pretty good approximation, and it's definitely good enough for drawing ray diagrams like these where we just want to understand qualitatively what's happening. Now, if you recall from the video, as I moved my hand closer to the lens, at some point things went crazy. So that means there's some special point right here. And then when we got closer than that point, we got the other type of image that was not inverted. And so this special distance is a property of the lens. It's called the focal length of the lens. And so now I'm going to draw the case where the object is closer than the focal length of the lens. So again, I can draw my on-axis ray as usual, and an off-axis ray. And instead of having the super long skinny triangle, now I have a much fatter triangle. In other words, it's a much broader cone. This triangle is, this cone is so wide that the lens can't bring those rays back together. It tries really hard, but it can't do that. It can only do kind of that. So here's what the ray would have done by default if there had been no lens. And here's what it actually does. It bends somewhat inward, but not enough so that it can be reunited with the other ray. So then, if our eye sees these rays, it traces them back to someplace far back. The dashed line trace back of that one goes back to there. That one traces back to there. And we get a virtual image at that distance. And then to see why that image is uninverted, we'll pick another object point which is off axis, and because it's easy, we'll draw the ray that hits the center. That one's approximately unaffected by the lens. It comes out over there. Now, the dashed line traceback of this ray is that it appears to have come from somewhere back over here above the axis. Cheat a little bit there. And then if I wanted to draw the other one here, I could draw that, but I know that it would have to come back to some point, to the same point. So here we have the two different types of images that we can get from a converging lens. We can get a real image when the object is farther than the focal length, or we can get a virtual image when the object is closer than the focal length. If we now bring back the one from the buffalo, these are all the different types of images you can get with lenses. So there are three possibilities. You can get a real image made by a converging lens, a virtual image made by a converging lens, or you can get a virtual image made by a diverging lens. You could imagine in principle there would be one other case, which would be a real image made by a diverging lens, but that's never going to happen if the rays are coming from an object, because if the rays are coming from an object, they're spreading already when they hit the diverging lens, and the diverging lens is only going to spread them farther apart, not bring them back together. So there are these three cases. So you don't have to reinvent the wheel every time you do a problem. Once you've done one of these, you can go ahead and just write it down in your notebook or something and refer back to it. And there are also three similar cases for mirrors. They work out the same. Real with a converging mirror, virtual with a converging mirror, virtual with a diverging mirror. And again, you don't have to work all those out over and over again. Now let's get into the quantitative analysis of all of this. The main problem that we want to usually solve is determining this image distance if we're given the object distance. This brings up this issue of signs. In this class, I'm using the European sign convention, in which everything is positive by definition. And that convention is explained in my book, which you can download for free at lightandmatter.com. So I brought back my ray diagram of the buffalo because I was so proud of my cute little buffalo diagram. And so what we're going to have to do is we're going to have to figure out the trend of the variables. We're going to change this distance do, and then we're going to see what effect that has on this distance di. So there are really two possibilities. We could find that they vary in the same direction, meaning as one gets bigger, the other gets bigger. We could also find that they vary in the opposite direction, so that as one gets bigger, the other gets smaller. So everything I'm about to do on the ray diagram is aimed solely at determining that. And another way of expressing the same idea is in terms of these angles. There's this object angle, and there's this image angle. And so if the distances are like this, then the then the angles also go in the same direction. If the distances have the opposite trend, the angles have the opposite trend. So since I only have space to move my buffalo closer, I'm going to move it to there. Doesn't really matter how much closer I move it. This is a diverging lens, so I know that no matter how close I put this, I'm still going to get the same result, which is a virtual image. You do have to be careful with a converging device, because then if you move past the focal point, you'll get the other qualitatively different case, like virtual instead of real or real instead of virtual. So same tricks as before. Send one ray along the axis. That's easy. We'll be right on top of that black line. Then for my other ray, draw the one that goes and hits the same point. That's the trick for getting a reliable result here. And then I have the original black rays over here, which are like this. And when I change the rays, they're just going to go like this, as if they're rotating rigidly. So with mirrors, you get the scissors effect, but with lenses, you get the rigid effect. The red ray comes in down here, so the whole thing's going to rotate this way, and that means it's going to exit on top of the original black ray. If I now trace that ray backward, the fact that it swept clockwise means that its trace back is also going to rotate clockwise and come down to here. So the new object position O prime resulted in a new image position I prime. So when DO got smaller, DI got smaller. So that's that. The trend is they behave the same way. And if that's true, then it should also be true for the angles, and it is true for the angles. So in my original position of the buffalo was really far away, so this angle was super, super skinny. And then when I moved it closer, it got a little bigger. So theta O got bigger. And then the image went from there to there. This red angle is bigger than that black angle. So the trend of the angles is in the same direction, just like the trend in the distances is the same direction. There's an equation relating those angles, which is always going to have this form. I'm going to have theta F, theta O, and theta I. And the only thing that we need to determine is that there's a plus or minus sign there and a plus or minus sign there. This focal angle is a property of the lens. A stronger lens has a bigger number for its focal angle. When you go to the optometrist and get a prescription for your glasses, this is basically the number they're writing down. And it's in units of diopters, which are like inverse distance. The distances here are inversely proportional to the angles. So we need to figure out the signs of these things. And what we observed is that if we made one angle bigger, the other angle got bigger. If we make one angle smaller, the other angle got smaller. The focal angle, which is fixed, it's a property of the lens, can't change. So let's do an example of that. We're trying to figure out what arithmetic operation over here could result in the same result when both of these numbers get, let's say, bigger. Well, if it was addition, that wouldn't work, right? Let's just do a simple example to verify that that wouldn't work. Say it was 3 plus 2, we would get 5. If we now make both numbers bigger, it would be 4 plus 3, which is 7. But then this isn't supposed to change. This is supposed to stay the same. So the operation we want to do can't be addition. So that means those signs can't be plus plus. Also in the European sign convention, everything is positive by definition, so people actually do refer to a lens like this as having a negative focal length, but in the equations in the European sign convention, this is considered to be a positive variable, so there's no way we could have minus minus. That wouldn't work. So the possibilities now are narrowed down to plus minus and minus plus, and then the idea is that we're subtracting two numbers, making them both bigger, and the result stays the same. And if you're unsure about that, it's easy to check that using simple arithmetic. So for instance, 5 minus 3 could give you 2. And then if I go 6 minus 4, I made both numbers bigger, I could again get 2. So subtraction is going to work for our example because of this trend. So the whole purpose of this was to determine that it was going to be subtraction. So one of these has got to be positive, one's got to be a negative sign in front. Then we need to know which one is the plus and which one is the minus. Again, we're using the European sign convention, so this has got to be positive. That means the subtraction on the right has got to be one where we're subtracting the smaller number from the bigger number. Looking at the diagram, we can easily tell that the theta i's are much bigger than the theta o's. So that means that it's got to be plus on the theta I, minus on the theta o's. That result by itself could be all we needed, but in most cases we're actually interested in predicting or measuring the distances, not the angles. So the d's are just like 1 over the thetas. So we go 1 over the focal length minus 1 over the object distance and plus 1 over the image distance. So there are 2 steps here. Step 1 is to use the ray diagram to determine the trend. Step number 2, if necessary, is to use the sizes of these angles to determine which one's the plus, which one's the minus.